Welcome. I'm Tobias Lindaaker. I work as a developer at Neo Technology. We build this graph database system called Neo4j. I've been working there since 2007 now, pretty much since we started the company as a company. The product was an in-house product in another company before that, but I joined when we started the company. I want to share a story with you today. I don't want to talk too much about Neo4j, the product that we sell, although it is intricately linked to the query language Cypher that we built. So it'll be mentioned a few times. This is a story that has some history to it, so I'll go through a bit of history and then share some lessons we learned and some future opportunities that we're seeing, and a few interesting tidbits to think about. So once upon a time, a long time ago, in a galaxy far, far away, in the kingdom of Sweden, that's where Neo4j all started. It is actually legally a kingdom, even though the king has no power. Yep, best kind of king. There was this database. It had a few interesting things going for it. It was pretty fast. It was a navigational database. It was an embedded database. And it had a data model that was different from what was dominating at the time. And I noticed you're taking pictures, and I want to say that I'm fine with that. I should have said up ahead that if anyone wanted to take a picture while I'm on stage, go ahead. So it had this interesting data model that modeled data as a graph, where pieces of data are nodes or vertices in this graph, and they're all interconnected using relationships or edges. So it was interesting, but wait a minute, navigational, that's been done before. That was done in the 60s, and it failed completely when Boyce introduced SQL, and the relational databases completely crushed all other data models, right? So how come this thing could be navigational in the 2000s and be successful? That's crazy talk. Well, I like to think that the world has evolved a bit since those early days. In particular, what I thought at the time was the interesting differentiator was how we write programs. The object-oriented programming paradigm, in particular, meant that we could provide abstractions over the data in a way that we couldn't do before. So we could have an object-oriented API, a sort of domain-specific language, and the key word here is language. It's embedded, it's an internal DSL in an object-oriented programming language for dealing with graph data. I think having this language was a pretty key step for Neo4j being more interesting in its day than what the codazol systems were in their day, or in the day of SQL. But others have done this before as well. So I say that object-oriented programming was interesting, but there was, in fact, in the 80s and 90s, a movement to try to create object-oriented databases. Why aren't those, if I'm here saying that object-oriented programming was really good for navigational databases, why aren't these object-oriented, this picture is not really showing that, but why aren't these object-oriented databases completely ruling the world? Because they're also navigational. Well, I have a theory or hypothesis for why this is as well, and I think that in an object-oriented database, what ends up happening is that you couple your application domain to your data domain. So your application logic and your data representation is very tightly coupled. And what you do in a graph database is you have a clean separate layer for your data domain that's a different layer than your application domain. And this decoupling allows you to evolve the two independently, and it gives you an easier way to deal with your application. There's a third reason why I think that, that things happen when they did, and that is that our needs for data have changed. Data in the early 2000s, or starting in the 90s even, and today it's even more true, is more connected than ever before. So having a database that can deal with the connections of the data is, rather than just doing aggregations over uniform data, is more important than it was before. Data is also less uniform. We deal with lots and lots of data, because volume is bigger as well. We got more data than we do, and with having more data about and more information about things, we have more diverse data. So data is less uniform, which means that we have to have a different way of querying them and a different way of storing them. So the tabular way of storing data that SQL databases traditionally do, which they're awesome at, lends themselves really well to very uniform data, where everything fits in the same square table. But if data is not so uniform, a relational database is not necessarily as good a fit. So I think those are a few reasons why a new database could why new databases could arise in the early 2000s, where during the up until that time, pretty much no other data model was than relational was even. You couldn't even talk about having a database that was non-relational because that was crazy talk up until early 2000s. But then the whole of NoSQL happened, and around that time we thought, yeah, this database that we built that was not relational and that we've kept under wraps because it was crazy talk to talk about databases not being relational. We could probably go public with that. There was another weird thing with this database called Neo4j that had some interesting things going for it. I mentioned it was embedded. So what does that mean? It means that it runs in the same process as your application does. This is really awesome for the fact that there's no latency between your application and your data, because it's all in the same process, it's all in the same memory space. You got direct access to your data, no network hop, no nothing. But for the same reason that you wanted to decouple your, or similar reasons at least, that you wanted to decouple your data domain from your application domain, you kind of wanted to decouple your application service from your data service as well. So this, we found out as we started this company, and as we started selling this database management system to people, and to or companies, customers, that this was a big thing that they didn't really like. Just didn't sit well with how they were thinking about deploying their systems. They wanted a traditional model, and for good reasons, where you have a database server, and you've got a few application servers that talk to that database server. And you can update them both independently. You don't have to have downtime on your database server to upgrade your to redeploy your application servers. So while being embedded had some performance benefits, it had some really serious disadvantages as well. And this is where our story about the query language begins, because in order to this nice object-oriented API that we had didn't really, it was really good in an embedded setting, but once you go into a client-server model, it doesn't quite work well. So we tried a few different approaches. This is one of the first ones. I have years here in the bottom that you haven't seen. I'm not going to mention them, but they're there for reference if you want to look at them. one of the first things that we tried, because this was the thing that everyone was doing at the time, was RESTful web services. So we tried this. Can we take pretty much our API that we have, that we love in embedded? Because that's what we knew. We knew our API. We liked it. And we were good at writing these embedded applications with our database. So we thought, can we take this API and create a RESTful API for it, or an HTTP API? I'm a bit ashamed of calling this RESTful these days, because there are a few things that aren't quite RESTful. But then again, people use REST about pretty much everything that's an API of HTTP, so who cares? So we had this pretty simple naive API where you'd, this is a request for the relationships of a single node. It happens to have an ID called 367. It could have been anything. And then this gives us a list of documents that are representations of all of those relationships. And that representation is pretty much links for getting information about that. So it was very much hyperlink oriented, as RESTful services apparently should be. This was not very efficient. This was in fact pretty horrible in terms of efficiency. It was really good for exploring data. So if you were a human interacting with the system interactively and like looking at, I found this node, now I want to go explore. Really good for that in a web UI, but not so good for actual live queries from an application, because it was just too much back and forth over the network. All right, back to the drawing board. We tried, the next thing we tried was to have the user submit JavaScript code to the server that used our embedded API still. So send code to the server, uses our server-side API for getting data, emitting that to a result stream that gets written back. Better. Pretty verbose things that you send over the wire. Same things get sent to the server again and again and again. So we didn't end up with this in the product. What we ended up with instead was you pretty much took that code and deployed it with the server, and then you sent parameters, gave it a URI and sent parameters to that. It's still in our products today, still widely used, something we run into problems with whenever we want to change. But it worked. So this was around 2011. A few years before that, we had another idea on how we could query graphs. Because one thing we noticed was that most of the queries that we typically ran over the graph was about doing tree projections. So taking the graph and viewing it, part of it as a tree. And typically what we would do is find a starting point, one or a set of nodes, based on some search criterion. And then from that node, find a tree projection of interesting things, and then return the leaves of that tree. So we thought, well, we can express that using something that can be a pretty simple, straightforward URI, and just do a regular HTTP GET on something that looks like a URI-ish, and get that projection back. What looks like URIs and is good for tree projections? Well, XPath. XPath does exactly that. So we toyed with the idea of having some sort of query language based on XPath. This was I don't have the actual notes from the time, but I remember that it was something like this that we wanted to do. What we did with this idea was that we said, okay, there's only 6 of us. Let's see if we have some community partner that can take this idea and work with it and build something interesting and build this query system for us. One of our co-founders, Peter Neubauer, had a friend who he was working with who we got to know through a company that was an early customer of ours. His name was Marco Rodriguez, and he took this idea and created a query language called Gremlin. It was originally based on XPath. It looked slightly different because slightly different from the idea that we had originally, because Marco looked at our ideas and said, that's not going to be able to do all types of queries that you're going to want to do. This is limited to just treat projections. So he created a different system where you'd, instead of what we had in our idea, where what you do is essentially stepping over each of these slashes, you step over a relationship to a new node. So you're always positioned at nodes. In Gremlin, you alternate between stepping from a node onto a relationship and then onto a node, onto a relationship and then on a node. So you alternate between a set of relationships and a set of nodes. Ended up with this syntax of outgoing edges, incoming vertices, and that's where I got lost. Because what's the incoming vertex of an outgoing edge? It didn't really make sense to me. Still pretty good system. Still around today. Have evolved quite a bit since then. The first evolution was that Marco realized that having this in XPath is just unnecessary overhead. So he made it an internal DSL in Groovy, I think it started out with, where you pretty much do filtering. So here you would filter get all the nodes from the graph, filter. I actually have a pointer here. Filter based on they should have this label, they should have this name, then take the outgoing edges of those nodes, filter those on type, filter on a property, etc., etc. So it's based on this filtering and progression type of notion, and it has more interesting features than that. And what's even more interesting about Gremlin is the recent development that's happened. Where Aurelius, or actually now Data Stacks, I believe that's the name of them. Let's call him Aurelius, the group that did this, or the Thinkerprop group, which is the open source part of it, that did Gremlin. That they've evolved to, and that is to use to have an intermediate representation for Gremlin. And I think that is something they call Gremlin bytecode. I think that is something that is really useful because then you can put something, some other language in front of it that is easier to read, because I don't like reading these. And that brings us to why we why we decided, at least at the time, to create our own query language. Had Gremlin been where it is now, maybe we wouldn't. I still think that that Gremlin is hard to read and too dense. So I still think that that Cypher is a better language for querying graphs. But at the time, it was definitely true. I'll actually stop there and look at another weird thing that Neo4j did at the time. And that's the notion. So I said that when we searched for things, the queries that we did were, first you find a starting point, and then you do a tree projection for that. Those were the most common queries. How do you find that starting point? The original Neo4j didn't have a concept of indexes. The idea that the founders had instead was that graph is a natural index. An index is just a tree. We can do trees in a graph because they're just a subtype of graphs. So what you should do in this graph world that that is holy to us is you should encode your index as a graph, and then you start from a single well-known root node in the graph, and then find the appropriate index root from there, and then search through that index tree to find your actual starting point. This worked perfectly fine, but having all applications duplicate and implement their own logic for managing index trees, horrible bad idea. So we provided, the first step though is that we provided libraries for applications to manage these search structures within the graph. And then we looked at those abstractions that we created and realized that this is actually just a service that gives you, takes some parameters input, a key and a value typically, gives you a node back, or a set of nodes. Could we not implement that more efficiently using a system that is tailored for being able to do such search? So we implemented the same search structure service thing using Lucene. Which had some interesting implications to it with a system actually managing 2 databases, but in a single database. But that's beside the point. The interesting thing was that search structures in Neo4j was something that from the beginning was something that the user managed. The user had to explicitly update this search structure because it was a separate structure. It was not an index over the data, it was a search structure. This will be important later on when we talk about Cypher, our query language. So we created this query language. This is circa 2011 that we started working on building this query language. It actually was, interestingly, because since 2007 when I joined, being a compiler guy originally myself, I was saying, should we build a language? It's kind of fun. And the founder said, no, don't waste your time on silly languages. We're building a database. And then we hired this guy called Andres, and he said, I don't care what you say, I'm gonna build this anyhow. My jealousy aside, it's awesome that he did. And how did he do it? He looked at these. What we did at the time was that we spent a fair amount of time actually writing queries. Sometimes for testing interesting scenarios, and sometimes actually for customers who had, or community members that came to us asking for, how is the best way of doing this? And if it was interesting enough and novel enough, we would take some time and actually look at it and analyze it properly, the use case that they had, and we'd come up with, well, this is how you'd structure a query for that. And we managed to get a process for how we implemented queries using our Java API. And the process was roughly like this. We started with a drawing on the whiteboard of the part of their data domain that they wanted, or the part of the data domain that you wanted to query. Drawing that out, which are the nodes that we have, what are the relationships between here, where do we start? So here we maybe started the query, what we want to end up with is getting the code for it. So we create a drawing on the whiteboard, and then what we actually did for documenting this beyond the whiteboard, we translated this into ASCII art in code comments. All right. Now this starts to look like something you could actually, what if you could actually take this representation and create a query based on that immediately, rather than have an engineer sit and write Java code from it. So that's what Andres did. He took this, click, 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 and translated it to a more linear form, so that you wouldn't have to think about where do these arrows match up, because that's tricky to parse. Translated it to a linear form, It was still the same kind of ASCII art kind of thing. And that's the basics for the query in Cypher. So you match these, you match the pattern, you filter it, and then you return, project your result and return that. This is actually what it looks like today. At the time, remember those separate search structures was still what we were using. So you had to explicitly say, I want to start here using this particular search structure. So here I'd say, I want to start at John, which I find through the search instruction person, where I'm using the key name and the value John looks up this, these nodes. And then I can continue matching. I match all the friends of John, where John doesn't already know those friends of friends, and then I return the friends of friends. So this is a simple recommendation algorithm. So this was the first version of Cypher. It looked pretty much like this. I wouldn't, don't dare me to put this through a parser, because potentially it could have, there might be some newer things that I put in some parts of it. Okay, could do reads only. Second version, we started doing updates of data. So here we this is a silly example, but in the vein of carrying on from the previous example I'm doing, not only do I return the recommendation, but I also write in the database that, hey, there's a recommendation here. So we still start from the search structure, and then we match, and then we could create or return. But the search structures couldn't be updated. So if I'd created more nodes here that I wanted to put in a search structure, then later on wanted to be able to query on, say that I created ingested new persons, I had to separately, using a separate API, update the search structure. So a bit tedious. So we sat down in a room in Malmö in Sweden and thought about how can we change Neo4j, how can we change the graph model that we expose in a way that Cypher can do everything. No need for these separate APIs. Everything should go through Cypher. Interestingly, how we'd gone in roughly 2 years from don't waste your time on these silly language things to how can this language do anything. So we came up with what we called Neo4j 2.0, where we introduced mainly one new concept to our graph model, which was the label. So we allowed you to put a label on a node, and we used that from a modeling perspective. It's like saying, well, this is part of a collection, or this has a certain type. You can use it for a few things that up to your choosing. From an implementation point of view, it's key for letting us binding an index to that node, or putting that node into an index. So we allowed the user to declare that I want this combination of label and property key to be indexed so that you can do lookups on those automatically without having to explicitly say, I want to use this search structure. So here, we do away with the start clause. And we just say, I want to match existences of this pattern. And then the query planner figures out automatically, like the engineer would do when I drew this on a whiteboard, like I would do. I figure out where the start point is based on the information that I have. The query engine does it automatically for me. Awesome. I have information here saying that the name should be John of this person node. So I find that, hey, I have an index for that. Awesome. I can use that for finding all the John nodes in the database. And then, again, find the friends of friends, where they're not direct friends already. And another new thing, merge that recommendation, which is a create or a match or create clause that'll create it if it doesn't exist. All right, so now it's a good time to look through this language that we created. In this sort of basic level, what are the things and capabilities that we have? So the main thing is this pattern matching part, where you describe a pattern that the database should match, and the database will find occurrences of that pattern in your data graph. These patterns can be additionally augmented with predicates that filter the matches. So I think of these two, this pair of match and where, as the match is expanding the world that you're viewing because if I only have a single node, it's in the pattern, it's just all of the nodes that match that pattern. If I have a relationship, it's like the Cartesian product of all nodes with relationships between them. So so a bigger pattern means typically a bigger set of results, whereas the more things I put in the where clause, the fewer results I get because it's a filtering thing. So those are the basic. This is the main basic thing. And then, of course, you have to be able to project the results, return something from the query to the user. So we have a return clause, which can do the things you can do in SQL as well. Ordering, limiting, skipping, those kind of things. And of course, we also, as in from the second version of Cypher, we have the ability to create new data, to update existing data, setting properties, removing properties, and adding and removing labels. And also the ability to delete data, because data changes over time. So you can delete nodes, you can also delete relationships, of course. One thing that we noticed here is that something you'd typically end up doing is you'd, when writing Cypher queries, is you send a query to the server, you get the result back, and then what you want to do with that is, based on that data you get back, you want to query for more. So we thought, can we do some sort of simple subquery type thing where you can take the results from a previous query and do another query based on that immediately without having to do a round trip to the client side. So we came up with this with statement that turned out to be really darn useful. It's a very simple type of subquery where you got a first query and then a second query, and the results carry on through there. And it has the same semantics as return. It's just that the query carries on with the things in scope. And then we have optional match, which is just like match, except if there are no matches, it gives you nulls back for the newly introduced bindings. So it's match or null. And then merge is like a hybrid between optional match and create, where instead of if there are no matches, it gives you nulls. If there are no matches, it creates the data for you. Yeah. Another interesting idea that we had on the topic of interesting ideas that we actually implemented was, what if we actually required that you put the version of Cypher in your query, and we supported multiple versions of Cypher in the database server, then we can make changes to Cypher in future versions that would be incompatible with previous versions without breaking your queries. So we did that. It turned out to work pretty well, left us room for change, but not as much as we as language designers would have liked. I would have liked to be able to change things pretty substantially from time to time. But it turns out that users don't really want to, once they've learned the way, even if it wasn't the best way, and we've done user studies on this. This is awesome to be able to do that. We've actually, this has allowed us to actually get feedback from a user and then improve the language. But even if we do have the ability to do that, users don't want to have to relearn. So we haven't been able to get quite as much back on this investment as we would have hoped. But it was a useful thing. Other things that we've done, of course, is we do optimizations on queries, and some of those optimizations take a bit of time to compute. But the realization that, well, you submit the same query multiple times. This is the same thing that pretty much all databases do. We use a cache of queries. So we compile the query once, and then we use parameters. You can still have parameters, and to parameterize that query, and it will be the same compiled query, but we amortize the cost of compiling it over multiple using that query for actual querying things multiple times. I think I'm gonna skip this and this and go on to this. So there are interesting things about language design in that you realize all the mistakes you made, and those are interesting to talk about. So there are a few warts in Cypher that some of them we're working on fixing, and some of them we haven't really figured out how to fix yet. This is one of those things that we know is problematic, but we don't, or two of those things, but we haven't really figured out how to solve it yet. The first two queries look extremely similar, yet they return very different results. The first one returns as many rows as there are measurement nodes in the database, and it returns the absolute value of each of the value properties for that particular node. The second one, while looking extremely similar, does something extremely different. It actually does aggregation and returns only one row containing the average of all the values. So we got two things that look very similar doing very different things. I'd like to fix that, but I haven't figured out how yet. The second one, which one is this? Oh yeah, let's skip that one. Yeah, this one is interesting. But this one is even more interesting. Can someone guess what the difference between these two queries is? In terms of actual textual representation, the only difference is that here I've broken up the pattern into two match clauses. It's the same pattern, but broken up in two match clauses versus in only one. Nope, it's actually a difference in semantics.
In the second one, A can be equal to C.
Yes, that is the difference. So the first one, in a database with this data, would return no rows. In the second one, we would return A bound to X, B bound to Y, and C bound to X as well. It is not actually the node bindings that are allowed to be different. It's the relationships. So what we don't allow is within a single pattern for two relationships to bind to the same relationship in the database. This is a mouthful to explain and has bitten people countless times, but also quite useful. Being able to have that, to make that difference is useful. It's just tricky to find a good way of expressing it. Another thing that's tricky to balance is how much syntactic sugar do you put in a language. And this is true for any language versus having just one canonical way of expressing things. So here, the first case would be the canonical way of expressing match all the nodes where the foo property has the value bar. And we've allowed a shorthand syntax for that, where we use a JSON-like notation for the property values of that node. There are other graph query languages. One interesting one called PGQL from Oracle that's being developed at the moment. I don't think they have it in product yet, but they have some interesting research prototypes on it. Has the ability to express even more complex predicates within the scope of a single node. This is not something we allow in Cypher, because we sort of drew the line there with saying that the first form is useful because it actually makes things shorter. But the second form is when you start allowing putting that many things inside of the brackets, when you have a bigger pattern, it ends up obscuring what the actual pattern is our reasoning for why we decided to not allow the second one. But it's a tricky balance of where do you actually draw the line. And there are cases where it actually would be useful to be able to express things within the brackets. Other useful things we learned rely heavily on parameters so that people don't compose strings to form queries, because that has caused tons of problems in SQL. And the last thing I want to talk about is what we are now working on, which is to open up Cypher. We've invited other vendors of databases and other types of tools that do graph querying. And we're creating what we call Open Cypher, where we are working towards sort of standardizing Cypher. We're relinquishing some of the control. We want to have an open platform where people can collaborate on improving Cypher and creating the next version. Yeah, so this was the story that I wanted to share with you. And unfortunately, I only had 40 minutes to do it. There's only that deep that you can go within 40 minutes. But the beauty of the tradition of storytelling is that the more times you tell a story, it changes. So I'd love to talk about this story with each and every one of you in the hallway afterwards, where you can ask me any question that you like. Thank you.